Let's apply the method of differentials to approximate the change in z to a slight application problem. In this problem, we have a cone of radius 6 centimeters and height 4.2 centimeters, and we want to approximate the change in volume, right? So there's our change in volume. That's what we're going to be looking at. If the radius increases to 6.05 centimeters and the height decreases to 4.12 centimeters. Compare the actual change in volume. Okay, so first thing I want to do is I want to figure out my differentials for my variables. But before I even do that, I can't write x and y. I need to think a little bit about this. If I want the volume of a cone, the volume of a cone is a known formula from algebra. It's 1/3 pi r squared h. All right, so I have a radius and I have a height as my two variables. So I need to know what my dr is, and I need to know what my dh is, because I'm going to need those for the differential method. Okay, so dr would be 6.05 take away 6, so that would be 0.05. dh would be 4.12 take away 4.2. Notice it's decreasing. Oops, that's a 1, 2, and that makes it negative. All right, so we have those two pieces. Now we're also going to need the derivatives. So we're going to need v sub r, because that'll be part of our differential formula. As a matter of fact, actually, let me write the formula real quick. So this is a formula we know right here. We also know that dv will be v sub r dr plus v sub h dh, right? Just taking the formula we have and applying it, right? I don't know if I should box it. It's not the answer, but I just want us to recognize these are the formulas we're going to be working with here. Okay. So I'm going to need v sub r. So the derivative of this with respect to r, I would bring the 2 down. So it would be 2/3 pi times r h. And v sub h would be equal to, well, if h is the only variable, then it'd just be 1/3 pi r squared. Wonderful. So again, these are at any point, right? The differentials at, or the, not the differentials, the derivatives at any point, the partial derivatives at any point. We need our particular point. We need the derivatives at our particular point, which was 6 and 4.2, right? Because that's our starting point. Okay, so v sub r would be equal to 2/3 times pi times 6 times 4.2. And obviously I'm just going to make a computer do that. And then v sub h would be 1/3 pi times 6 squared. Okay, so let me go grab Maple. Again, I had it verify my derivatives were okay, which they were, and then I told it to evaluate the derivative with respect to r at these values, right, 6 and 4.2, and it did, and then I just copied and pasted, even though technically h is not involved in the second one, and it gave it to me. It's actually 12 pi. If I want a decimal approximation, I can just tell it to give me a decimal approximation of that value. Oops, oh, that didn't, there it is, 37.699. Actually, I boosted it to 10 digits so we could see. Okay, so we're going to go put those two values in right now. This is 12 pi, which is about 37.69911. And this one was about 52.77876 or so. Okay, so now putting it all together, the differential method, right? dv would be equal to this number, right? 52.77876, so 52.77876 times that value up there, 0.05 plus 37.69911 times negative 0.08. And then obviously we're just going to make a computer do that. And I already did. And we get negative 0.37699. So if I rounded to 3 decimal places or something like that, it'd be 377. I think I'll go the whole way. I'll go 37699. Good enough. And that'd be centimeters cubed because, of course, this is a change in volume, right? dV is change in volume. All right, so this is the approximation. Now, they wanted us to compare to the actual change. Okay. Okay, so we can do that. The actual change delta V, right, change in volume, would be equal to, actually, let me write it out, just so, change in volume, right, because all the work up above is trying to get the approximate change in volume, which we have. So the actual change in volume was V of 6.05 comma 4.12 take away V of 6 comma 4.2. That'd be 1/3 pi times 6.05 squared times 4.12 minus 1/3 pi 6 squared times 4.2. And of course, we just make computers do this. We are not going to do this by hand. That's just insane. So let's see, it's right here. I actually did each piece separately. So there's the beginning, there's the end. And the difference was negative 0.4164705. And that would be centimeters cubed again, because this is volume, right? So centimeters cubed. And they're relatively close to each other. It's not great. I mean, they're a bit farther apart. So the approximation is close to the actual change. But it's not close within an order, it's close within an order of magnitude. But, even the first decimal places are not the same. But again, that might be close enough for what you're trying to do, right? So sort of close, right? So 0.376 to 0.416, right? 377, right? So they're both about 0.4. They're close, but they're not super close. They're not as close certainly as the last example was, where they were the same decimals for the first 3 decimal places or so.